Let me show you why we achieved a really important step. First, I rewrite the second term over here in this way, where I split x 1 to t minus 1 to z t minus 1 and z 1 to t minus 2. If you compare this with our formula from the very beginning over here, you can see that this term here is exactly the belief from the previous time step t minus 1. Now we can rewrite the integral with the belief xt minus 1 inside. The amazing thing is that we have a recursive update formula. You use the estimated state from the previous time step for the prediction of the current one. This is one of the most important steps in the recursive Bayesian filter, because we are independent from the whole observation and control history. So in the graph structure, I replace this part over here with the belief xt minus 1. Finally, you can replace the integral by a sum over all xi's, because you have a discrete localization scenario in this case. By the way, you already saw this formula in Sebastian's lesson for localization. The process of predicting xt with the previous beliefs xt minus 1 and the transition model is technically a convolution. Now you also know the full mathematical background and how to derive this module. If you take a look to the formula again, it is essential that the belief at xt equals 0 is initialized with meaningful assumption. It depends on the localization scenario, how you set the belief, or in other words, how you initialize your filter. For example, you can use GPS to get a coarse estimate where you are. So let's sum up to this point. You learned again how to apply the law of total probability by including the new variable xt minus 1. You also learned about the Markov assumption, which is very important for probabilistic reasoning. And finally, you learned how to derive the recursive filter structure. Next, you will implement the motion model in C++. You will also learn how to initialize our localizer, which means defining the belief of the state at the very beginning. So, let's do it.